Thank you very much. All right. Yeah. Thank you very much. This talk is going to be largely an overview. It's about a project that's still ongoing, and it will go on for another 6 months, which is another way of saying that some of the things that I will be mentioning haven't really been worked out fully. It is also a very large project that involves a lot of people. And as is the case, I suppose, in most, if not all of these projects, one single person doesn't understand all the pieces. So I will give you an overview, but I will concentrate on the piece that I know best, namely the linguistic and ontological side, the knowledge modeling part. But I do want to give you an overview, and forgive me if it is a little rushed at times. So this project is called Kyoto for 2 reasons. One is that we conceived it actually in Japan, in Kyoto. And secondly, the domain of the application that we are interested in initially is biodiversity and nature preservation and environmental concerns. So we had to struggle to find this acronym, Kyoto Yielding Ontology for Transition-Based Organization, a bit awkward. It's funded by the European Union, the 7th Framework, and as you can see, it involves a number of institutions, including Masaryk University, our local host, and people not only from Europe, but also people from Asia, from China, Taipei, or Republic of China, and Japan. And importantly, it includes not only academic institutions, but also what we call the users, 2 groups of nature and environment institutions. So the World Wildlife Fund, which most of you probably have heard of, and the European Center for Nature Conservation. So we are actually working with domain experts. What is Kyoto? Well, it's the idea is to create a rich, flexible information system that is more informative, more rewarding than what you get out of a regular search engine or question-answer system. We do open text mining and, as I will try to explain, deep semantic search, deeper, again, than what you get in most current systems. And we create a platform for the acquisition and the maintenance, curating, and sharing of information across currently 7 languages. And importantly, the system is dynamic. It is getting updated and maintained continuously. As I already mentioned, our concern currently is environmental protection. So we are interested in data about endangered species, landscapes that may change as habitats for certain species, either become more hospitable or less so, and of course the human impact on the environment. And related to that, the growing and shrinking population of certain species and endangered species. But important to stress, the system will be extendable to any domain, and we designed it like this on purpose. And early on in the project, we had a meeting where we gathered not only representatives of our 2 user groups, but also people who work for other institutions and who are concerned with environmental protection. And we asked them, we said, how do you work? How do you go about finding out information? How do you share the information? How do you update it? How do you store it? And so forth. And we were actually a little bit shocked at the what we would call lack of sophistication, we in the knowledge engineering business, with which these people proceed. They are, first of all, not very technology savvy. Some don't use the web at all. They tend not to share information, not only across institutions, but not even with their colleagues in the same institution. If they share, it is done very informally over coffee in the hall when they run into each other. And when we said, well, why are you doing this? And why don't you go about this in a more systematic way? They said, well, there is just too much information. We just can't handle it. And we really do need your help. So this was the positive news, that they're very eager for people to provide an information system. At the same time, given all this, the bad news or the lack of sophistication in information sharing, we must keep in mind that these are people who are approached by governments to give expert advice that may have long-ranging and important consequences. So it is really an important concern. So we all know there's a lot of information out there, but as we know, it comes in different formats, different structures, on different locations. It is not always distributed along the same channels. Sometimes it's accessible only to certain groups. There is the linguistic, the language barrier, that certain information is available only in certain languages. The translation services are mixed. For an expert text, you can often understand what the main point is of a document if it's been translated automatically, but often it is not satisfactorily translated. Information, of course, is forever growing and changing, and has to address a wide range of experts, some of which I mentioned here. Certain situations, especially in the environmental domain, require very fast intervention, not only locally, but often on a global scale. So landslides, earthquakes, fires that may endanger entire populations of plant and animal species, may have disastrous consequences for the economy, tourism, and so forth. So what the experts tell us, and what is obvious, is that efficient communication is needed, up-to-date information, both on the expert level and also on a level that can be communicated to government institutions across long distances, across languages. So our goals are then to develop a system for sharing such knowledge, for identifying, storing, retrieving, and distributing information, to make it reusable, to make it shareable, and to make it dynamic. So once we have identified a certain a topic of concern, an area of concern, information about that species or area or phenomenon or process should be updatable. Our ambition is to perform really deep semantic analysis, and I will explain a little more what I mean by that. To link the documents to multilingual lexicons, word nets in fact, and to a language-independent ontology that clearly represents the concepts behind the linguistic expressions, and that is machine tractable. The system should address both experts and laypersons who can actually manage the system, especially the kind of people that I mentioned earlier who are not technology savvy. We need to address a number of limitations of current search engine. One that's well known to, I'm sure, all of you in the room here is the famous lexical ambiguity, which also translates into the areas of concern for our project. So the bat has at least two meanings: a baseball bat, the winged mammal; field, the an area, as opposed to field of study; plant, an organism or a factory, and so forth. Also, in documents, of course, the reference to the same entity may vary. There may be synonyms or hyponyms, more general terms, and so forth. So we want to capture all of this and use it in an intelligent way that will structure the document and the information and make it available. Our system is based on incremental learning, based on search results. I will explain this a little bit more. It is based on merging documents that have overlapping information, on automatic updating of information, and on the detection of relevant new information, and a component that will actually alert a user of a previous document that something has changed that is relevant to the information in the document that he or she accessed before, but that one variable or two variables in the way we structure the information has been modified, has changed by additional documents. So how does Kyoto differ from existing data mining software? Well, first of all, we have the cross-lingual aspect. The whole system is developed for different languages in a way that combines the information, unifies them, and makes them equally accessible in different languages. Even though we are working on a specific domain, the system is designed to be domain independent. It is independent of knowledge, engineering, or technology background. And as I mentioned earlier, we have a very sophisticated, both language dependent and language independent knowledge base behind the whole system. Our requirements for our architecture were to represent a terminology and to curate it by means of a wiki platform, a wiki environment that allows experts to determine and encode knowledge about concepts in their domain. Yet these experts are not knowledge engineers. To anchor the relevant terms in an ontology, as I already mentioned, which in turn is linked to 7 languages. These are the languages that we are currently working with. Not only the standard sort of European, Western European type languages, but also Basque and Chinese and Japanese. The key components that I will walk you through quickly in the system are a wiki platform called Wikioto, two important components called Tybots and Kaibots, robots that are on the one hand extracting terms, and on the other hand the Kaibots extract what we call facts, and I explain why I'm putting that in scare quotes. And a system that is not yet fully developed, so I will not say too much about it, a fact alert component that detects and reports changes. Oh, oops. I have a very fancy picture here, which should be, okay, it's coming, it's loading. Okay, I see, okay, sorry. It's coming out, okay, good. Okay, so here I'm showing you the whole thing here, and it looks kind of a little bit overwhelming, but I will repeat this graph several times. I will walk you through in counterclockwise fashion, and I will focus, as I mentioned, later on the ontology and the WordNet part. But basically, we have experts or users who specify documents, search documents in their various languages. We have the Tybot that I already mentioned, the system that detects relevant terms, and I explained what I mean by term exactly, feeds them into the system. Experts can review these Tybots, assign them not only to the WordNets in the 7 languages, but also to the domain ontology, the lower ontology. The knowledge-yielding robot is the one that extracts what we call the facts. And again, this is done on the basis of the information about the terms and the way people in this platform encode snippets of facts or propositions or statements. I will explain what they are. These get indexed, enter into a text and fact index, and then the user can actually undertake a semantic search and for the relevant documents. The whole thing is dynamic. This goes on over and over again. And obviously, the more cycles this has been run through, the better the individual components will perform. The Tybots learn better to extract all and only relevant terms, and the Kaibots get better at detecting what we call facts. As I said, I will explain all of this in more detail. So the first part is what we call capture, or it's extraction. We have a server which allows the user to select and store documents in the Kyoto document database. And it includes linguistic processors, both low level and somewhat higher level, that produce linguistic annotations. The domain experts work in the environment which is called Wiki Planet, where they upload the documents from multilingual sources and submit them for analysis. The texts are processed with the usual pre-processing, in the usual pre-processing steps, so morphologically, syntactically, and more ambitiously semantically. So we do lemmatization, part of speech tagging, and chunking, all of this language specific because the documents, as I mentioned, come from different languages. And this is stored in the CAF Kyoto annotation format. This format is compatible with other formats that are ISO compatible. So we make sure that they will be useful for future generations and worldwide, of course. So on the linguistic level, the annotation level, things are pretty straightforward. Tokenization, part of speech tagging, and so forth. Here's a quick overview. Here's the sentence. Tropical terrestrial species population declined by 55% on average from 1970 to 2003. The first run-through gives you a word segmentation. The second run-through gives you a chunking or a term, so it chunks together the 55% rather than 55 and per and cent if it is so spelled. And another step chunks candidates for whole terms, so terrestrial species populations, and tropical terrestrial species. So notice, of course, that here you have two possibilities and of combining the constituents. So this is all fairly straightforward. Notice that for a linguist, of course, these terms like terrestrial species and terrestrial species population and so forth wouldn't necessarily be units, wouldn't be linguistic units, since they are compounds that are semantically transparent or compositional. But one of our concerns, of course, is precisely to capture those terms or chunks of terms that keep reoccurring in the text, in the documents of interest. And we don't really care whether a linguist says this isn't a word. This is really a compositional compound. Also dependencies. So, for example, the output of this processor tells you that chunk 4 is the subject of 5. So population is the subject of decline. More difficult, the semantic annotation in CAF, the usual problems that I think many of you are familiar with. Named entity recognition is relatively easy. Much harder, of course, are semantic word sense disambiguation and semantic role labeling. This is the second level of the CAF annotation. So here we have the word sense disambiguation problem. We have a word like population, and we look in WordNet, in this case in the English WordNet. We have 3 relevant senses that we have identified, and we have to figure out which one is intended. We do this, of course, statistically, derive a confidence level. And the way we are doing it at the moment is the way many people do it. We're exploiting the WordNet structure. So we are, if you're familiar with Ted Pedersen's work, he compiled different variants of word sense disambiguation algorithms based on the relatedness that WordNet expresses in terms of hyponymy, meronymy, antonymy, the definitions, and so forth. So you can reasonably well distinguish homonyms, so plant, the industrial plant from the plant life. But when it comes to finer distinctions, the WordNet algorithms don't work all that well. So at the moment, we are experimenting with a mix of using information from the domain WordNets, the very specific WordNets, and the generic WordNets, which are not specific to the domain that we are working on. But like everybody who has worked on words since disambiguation, there's no 100%. Easier to annotate are named entities, species names, for example, names of locations, geographic names, which we can identify with the help of large databases. These can be linked to the WordNets and from the WordNets ultimately to the ontology, to generic superordinates such as country or mammal or something like that, and thus can be translated directly or linked directly into the knowledge structure in WordNets and the ontology. So here's again our picture. We've just uploaded the documents, we've processed them in CAF, and we're now going to look at the tybots. So the annotated documents are input into the term-yielding robots, the tybots, which learn to extract domain-relevant terms, or really chunks and large compounds, and their relation, semantic relations to other terms. So whether they're more general hypernyms or more specific hyponyms and so forth. And the tybots also learn by trying to figure out these relations to integrate the terms that they detect into the WordNet hierarchies for the 7 different WordNets. Now, how do the tybots do that? Well, they have several mechanisms. One is they simply detect that something is a term or guess that something is a term. Statistically, if certain words separated in English by empty spaces co-occur very, very frequently, they guess that this is an expression, a term, a compound that should be treated as a unit. From the point of view of understanding the semantic relation to other terms, they employ the lexical patterns that Alan Cruz first found and that Marty Hurst wrote about, that things like such as or and other that clearly distinguish super from subordinates, for example. Most importantly, the tybots learned from the Wikioto knowledge base. So I will now move on to the Wikioto knowledge base in a minute. As I already said, the terms are usually compounds, often semantically compositional, and they form the basis for extending the WordNets, because the WordNets in the 7 languages currently exist only in the general domain, and new domain WordNets are being built up from the tybots. So I will now move into the Wikioto, which is the concept and fact curating and creation module in the system, and from which the tybots, among other components, learn. Okay, let's see. Oops. So the Wikioto is what you might call a knowledge editor, and the domain experts curate both concepts and facts. And I'm putting this in scare quotes because philosophers always jump at me when I use the word concept, but permit me to use it in an informal way to refer to a notion that is expressed often, but not always, linguistically by a word. Fact doesn't mean fact in the sense that it is logically true, but it is a proposition, a statement, or a chunk relating several entities to one another in terms of an event, a process, or a quality. The users create what we call knowledge profiles, and I'll give you some examples in a minute. These are patterns of both linguistic and conceptual and linguistic information. These can be language-specific or language-independent. The Wikioto has 3 components: a document manager, then the term and concept editor, and also the fact editor, which I will come to later. As far as the concepts are concerned, the domain experts select them, agree on their meanings among each other, and agree on their representation both within the language and across language. And this is important because ultimately these terms have to be entered into, or have to be made compatible and readable, interpretable by an ontology. So here's an example for some examples for a concept schema, a profile, which an ontology can read. So climate change is a subclass of change. It has it's an event that has a cause, and the event is the climate change. I will return to some other examples in a minute, but just to show you the format in which this is represented. The Wikioto user browser also allows searching the terms and adding new terms that the Tybots has not necessarily contributed. So the user is free to add their own terms. Moreover, terms can be imported from databases and structured resources. So there are domain-specific thesauri that are already out there, ontologies, generic word nets, of course, species database, and DBpedia that are relatively easy for the users to integrate into the system. As I said, some of these resources can be automatically loaded, especially if they are in a format that is already hierarchically structured, as some of them are, and is therefore compatible with WordNets and an ontology. In the ontology and in the WordNets, a knowledge is distributed over 3 layers in order to not duplicate information, but also allow clear linking from more general to specific concepts. So there are generic word nets, such as English. There are language-specific word nets, and there is a language-independent central ontology. So just to sum up what's happening in this Wikioto, the users can create these conceptual patterns, language independent. Here's another example: organism invading coastal area. So the system scans the texts for terms that matches the terms with words, for example, in the database or in the already existing term database in Wikioto, tries to find a match in the generic word nets, travels along the hierarchy in the generic word net until an ontological class is identified. These ontological classes are much more abstract, much sparser than the generic word net, so go from here to here. This is an error-prone step. The system verifies that the class is compatible with the pattern, seeing whether other patterns have been entered that are part of this class. And if yes, then the pattern will be added to the fact database with pointers to, of course, the documents. So we are now, bear with me. We have now talked about the Tybots. We've talked about the Wikioto, what is happening here. The users look at the terms in all these languages, create their own terms. Now it's important that the users only, to note that the users only have access to the domain ontology. We don't let the domain users, the environmental folks, touch the upper level ontology, which was designed by a trained logician, philosopher, so this takes special skills. Nor do we actually let them touch the middle ontology, which corresponds on the linguistic side to what many of you know as ordinary word nets. So here are words that are used by all of us every day, but we keep this part stable, at least as much as possible, and let the the domain experts work only on this level and create this level on the both linguistically and give input to the ontology correspondences for the linguistic expressions here. So we are now going to look at the KaiBots, at the fact extractors. How am I doing for time? Okay. So knowledge-yielding robots, we call them. They create and store what we call fact patterns, again, language independently. And we call these patterns knowledge profiles as opposed to just term or conceptual profiles. Like the KaiBots learn these patterns, look for similar facts in the document base, and relate to the word nets in the different languages and the domain ontology. The output is a richly structured annotated text repository, a database of facts and relations that match the patterns. So here's an example. If you look at a pattern like dramatic increase of snake population in rural Spain, the system derives a pattern consisting of decreasing process, having an effect on number of snakes and habitat Spain. And is looking in the documents for matching snippets. I can't go back now. Okay, sorry. All right, what did I do? Sorry. Okay, I did go back. All right. One thing I should mention that the search is not only done literally for these snippets, but it is also using on the word level or on the snippet level for more generic, for more general and more specific patterns. The KaiBots then index these facts, and they're very strictly structured. We have 4 variables for aspects of facts that we try to encode. One is the what or who, or topic or theme, or what is involved. So snakes, for example, in the previous example. What is the event, or what is the process? And important time and location. So carbon footprint of Spain, 2000 to 2009, would be a piece of information that you might find in a document that can be analyzed according to those 4 points. The facts then are made accessible via a semantic search, which is basically the search that the user of the system then undertakes. So we have fact tables. Liven up my talk. You see some more examples here. This is how the data are structured. They're structured very, very rigorously that way. And you might ask, why did we pick those criteria? Well, these come again from the domain users. That's what they want to know. They need to know what's happening to whom, where, and when, and often, not always, what is the cause. And they said that's what they're looking for. That's what they need to be structured. So the KaiBot extracts also causations. So it's looking for patterns like A causes B or A is a factor in B. It's looking for patterns that involve the words increase and decrease and hyponyms and synonyms of these words. Importantly, it is also using for quasi-identity relations, patterns such as X such as Y's, X acts as or behaves like a Y, X can be seen as or considered as a Y. These are all very important lexical semantic patterns that the system has to rely on. Everything gets stored in a text and fact index. So, for example, an elephant is associated with entries showing not only the related terms in WordNet and in the ontology, all the terms that are related to the syn set, the synonym set containing the word elephant, the extracted words and phrases denoting relevant terms, referring to properties, processes elephants are involved in, locations where elephants live, and so forth, and phrases containing the substring elephant or synonyms or hyponyms, and ultimately, of course, the websites where any of this information is mentioned. These cycles are repeated, as I already said, and the individual components, the term extractor and the fact extractor, learn from continually enriched knowledge base, the Wikioto. Just to make it a little more easy to get an idea of how the system works, so again, we have our documents, we have the capture server, where experts select documents, feed them into the document base. The documents get annotated with syntactic and semantic annotation in the CAF format. And then we have our two extractors. On this side, the term extractor, the TyBot, extracts the terms. Humans edit the terms, and they either and the terms get represented both in the domain WordNets on the linguistic level and in the domain Ontology on the abstract concept representation level. On this side, on the fact extraction, the TyBot goes to work, creates and works with these profiles, these chunks of information structured according to the criteria that I mentioned. If they pass muster, they enter into the document base, the fact base, and a person who curates them is constantly monitoring them. Just as here, the person in the Wikioto is monitoring the concepts and the terms. So that is the overall picture. Finally, on the sort of output side, the semantic search, the knowledge that is mined from the document, as I mentioned earlier, can be or is intended to be used not only by experts but also by ordinary people. There is a user-friendly natural language query possibility on a platform we call an environment called Wiki Planet. And unlike Google, I hope I have convinced you implicitly that we are doing much more than Google, or we are trying to do much more than Google and other information extraction systems. We organize the results, we structure them semantically in a very rigorous way, and of course we have the cross-linguistic ambition that really intelligently gives information in the different languages. Note that even if a user has not specified one of the knowledge chunks that we consider important, ingredients like time or place, he or she will get them anyways, because that's how we structure the information. So in the semantic search, all the events and properties evolving an entity of interest that the user may be wanting to find out about is searched. The search is repeated for all related terms, related in WordNet by WordNet criteria, and spatial and temporal properties are added. So, for example, if you query polar bear, you get all properties or processes that polar bears have been associated with. So, extinction, fertility rate, you always get it with respect to location and time. You get the documents where these were referred to, or a subset of these were referred to. The user can select, filter, combine, throw out the information. He can restructure them, can select a subset of documents, and importantly, our users rate the usefulness or the relevance of documents to search. So they themselves, either on an individual or on a community level, can fine-tune the system according to their needs. What we haven't done yet is this fact alert, but we hope to do this in the remaining 6 months, an automatic notification to the user or to the system if any of the variables that we encoded for a piece of information, such as time or a process or location, has changed for a given topic. Now, okay, I would like to focus on this part, as I promised, a little bit more, because that's really the part that I'm concerned with, or my group in Berlin. Everything I've told you up to now is something where I've had a little input, but am not the main responsible person for. So to represent knowledge, we need to consider two faces of really the same thing. One is the linguistic side and one is the conceptual side. And these are represented on the one hand in word nets, on the other hand in ontologies. So word nets, semantic networks, are concerned with language, not with logic. Language is very useful, but it is not a logical system. People don't naturally think the way logicians think. They have to be trained, or it has to be elicited. But language, of course, arises spontaneously, and as we know, there is a lot of variation across languages. Which concepts are being labeled is not at all a universal process. But WordNet tries to capture what is labeled in a language. So here's a snippet of a WordNet. Is actually a more an enriched WordNet from the one that you may be familiar with from the Princeton WordNet. But you have not only words, which may be organized into synonym sets and organized according to, for example, here the is a relation, here the is a relation, but also semantic roles. So this is again something we are still working on. Those of you who have looked into semantic role labeling know that the first challenge is to find the right inventory. You want the inventory to be descriptive and satisfactory for your purposes, but you don't want too many semantic roles, so you want them maximally distinct and not overlapping. But things like patient and agent, state, procedure, location were found to be relevant to our domain and will be encoded in the word nets, or will be retrievable. Now, the 7 word nets for the 7 language in the Kyoto system are all linked to a single shared ontology. And as I already said, the ontology deals with the conceptual level and provides a language-independent representation of the knowledge that is encoded by the words in the individual languages. So while a given word in one language is not necessarily represented in the word net of another language, it is represented, or it must be represented in the ontology. So the ontology is the union of expressions for all concepts, or the union of the concepts in all 7 word nets. And the ontology, of course, is also computer manipulable by a computer, and which can access the meaning of words, if you want, in any of the languages. Our ultimate goal that goes beyond this particular project, and that Piek Vossen and I have been working on for years, is to extend this ontology lexicon or WordNet mapping to languages, any languages of the world. And but it's exactly the principle that we have in Kyoto, where the ontology represents concepts here in an oversimplified manner, represented by English words. But English, that's an accident. There's nothing English about it per se. And the lexicons of many different languages that link to the appropriate concept in the ontology. The advantage here is that, first of all, some languages may not lexicalize, may not have a word for a given concept. So in this example, they all do. All languages seem to have, so German Zug and English train correspond, and car and auto, and so forth, and presumably the Italian, I should stop soon, and so forth correspond as well. But it's quite possible that one language may not have a word. It may simply merge these two concepts. This is okay. This can be represented in the language, but it poses no problem for translating from one language to the other via the ontology, because that the two words in one language will then simply match onto one word in another language, which is not linguistically making the distinction. I have to rush. Okay. So the ontology is a formal definition of concepts that a computer can use to make logical inferences. And the ontology is a logical construct. The Kyoto ontology was handcrafted by, as I said, a trained logician, Amanda Hicks. It is compatible with other ontologies that have been proposed, and that have been proposed also as connectors for the different word nets. But it was tuned to accommodate the particular domain of Kyoto. There are three layers in the ontology. If you remember that large scheme that I showed you, there is the top ontology, the very abstract ontology, the middle ontology, which often corresponds to real words in a language, and the domain ontology. The top ontology represents concepts that in no language that I have looked at are actually words. It's an extension of Dolce, the ontology developed by Guarino and Welty. As I said, it is highly abstract, and as far as I know, there are no lexical equivalents to these high-level concepts, but it draws very fundamental distinctions that later play out on the lower levels of the hierarchy. We distinguish three fundamental qualities or entities: abstracts, endurance, and perdurance. The middle ontology contains, as I said, what corresponds to many words in real languages, also qualities and dimensions. Perdurance refer to anything that's an event or a process or a state, as something related, in this case, to noun synsets in WordNet, such as extinction, and some endurance. The domain ontology contains specific concepts specific to the environmental domain. At the moment, we focus on estuaries. As I said, the user can edit the domain ontology. So the relations in the ontology among the entries, among the concepts, simple things like logical entailment. So a mudslide is represented as entailing a movement of Earth. Also participation, how an endurant participates in a perdurant. So there are nodes in the ontology that are called done by or performed by, and temporal relations and spatial relations. We also represent qualities, binary qualities like alive or dead, indefinite qualities like something that is always green or something, or measurable qualities like high or low or increasing or decreasing. Importantly, the ontology draws distinction between types and roles. This is something the WordNet does not do, and there's a real difference here between the linguistic level and the logical level. So a plant is a type, is a kind of organism, but an invasive plant is a role. So a given entity may be both. If I show you a wheat, it's both a plant and an invasive plant, but the distinction is that it will always be, anywhere in the world, be a plant, so that's a type, but it's not always necessarily always and anywhere an invasive plant. So role relations are time-dependent or location-dependent, whereas types are stable over time and place. This distinction is very important to Kyoto because in the documents you will often find news and the facts that the users are interested in, or the ultimate users, pertaining to role properties. So something was once something, and then now it is something else. Something that was once an invasive species no longer is, or something that was an ordinary species is now endangered. So it's very important to encode the role relations. We have developed a tool called Rudify, which automatically distinguishes between types and roles, uses these lexical semantic patterns that Cruz and Hurst, for example, worked on already, distinguishes between types like X's and other Y's, X's such as Y's. These can actually also be roles. This isn't 100% safe, but the role ones are definitely clear. So when you say X is considered, or Y is considered an X, or X Y used to be an X, these are always roles. We applied these patterns to large texts and tried to identify the appropriate terms in documents to enter them into the word nets and into the ontology. We also played with the cross-linguistic validity of these patterns, and surprisingly we found that they are not as universally valid, universal now really meaning only our 7 languages, as we had thought. So their applicability seems to be somewhat language dependent. I have to stop. We had a first evaluation where we again gathered domain experts, environmental scientists, and explained the system to them and said, now go and use it, look for information. And we also, it was a somewhat controlled experiment because we also had them use Google and said, how would you use that to extract the information that you're looking for? And our domain experts, I can say that confidently, rated Kyoto very high, higher than other search engines. They appreciated the semantic organization. They appreciated the criteria that we use to organize the facts and the terms. They appreciated the multilinguality. And as I said, the system, this gave us confidence to plow ahead and try to make the system extensible to other domains. We think that Kyoto at the moment is has somewhat unique qualities, and we are particularly proud of the fact that we have built a tool that can be used by people who are not knowledge engineers and that hides the complex linguistic and conceptual knowledge in a way that does not scare off an ordinary user while letting them use it. I think I have to stop. Yeah, thank you. Okay. Yeah.
Many thanks for this nice overview. My question is, I'm involved in this ISCRAM community, and when you are on the place of a disaster, one characteristic is that you have almost no access to internet, or bad access, or expensive access. So I was wondering if you also provide the functionality of resumes or choosing the most important document, so that I can have quickly information.
Thank you. That's very interesting. But how would the resumes be made accessible if not via some kind of computer? Only limited access. Yeah. Okay. So you have. Okay. I just want to make sure I understand your question. You have access to a computer, but you just don't have access to the internet or limited access. Yeah. I see. Okay. That's interesting. I haven't thought about this. Yeah. Thank you. I think that's wonderful. The only example I can give you off the top of my head is that, as I mentioned, I think in one of the slides, the users who work with in the Wikioto system and the people who are actually already using the system, doing the semantic search, can construct their own databases. So they can select certain documents and discard those that are not of interest to the area that they work in. So they could construct resumes or store stable repositories of information. But I'm saying this without having thought about specifically what you said. So thank you. I think that's a wonderful question. Yeah. Yeah.
You're assuming some quite heavyweight language processing tools for the languages like semantic role labeling and word sense disambiguation. I mean, that we have them for a number of languages, but would it be true to say that the system is still usable if you use those on source languages and then users from other languages that are less resourced could still use the system via the word net mapping and
Yes.
Simple queries that aren't analysed deeply.
Yes, absolutely. And I hope I wasn't being dishonest, or I hope I wasn't giving an all too rosy pictures. As you know, certainly semantic role labeling is very difficult, even for English, where it's done by many, many people. The word sense disambiguation, I'm a little more optimistic, or I think things work a little better even in those varied languages, because it so happens, as a self-selection really, that the people who participate in this project have well-developed word nets. But once you extend it to another language, then obviously, yes, then I suspect you will have to do some sort of a mapping and from a well-developed word net into a less developed one, or translate by some means, yeah. And then you will get some deterioration and noise. And we haven't done that yet. But thank you, that's a good question too. And that is one that will face us, or will face future developments of the system, yeah. And certainly, as I said, the word sense disambiguation, even with English, where the largest word net exists, is far from perfect. So, and this will this problem will get bigger as we move into other domains. Yes. Okay. Okay. Thank you.